Okay, so y'all see chapter 7?
Mm-hmm.
PowerPoint, okay. So let's just make sure y'all like know this here. So this is what we call artifact, right? So it could be any. What are your types of artifact? Y'all remember?
Yeah.
So it's a wandering baseline.
Mm-hmm.
Electrical.
What else?
Broken.
Somatic.
Yep. What else?
Broken.
Broken. Right. So you have different types of artifact. So if you say wandering baseline or somatic, those are two types of artifact, right? Because that is a question on the test. Knowing what is artifact and what are your different types you can have. Because when you look at this on a picture, so if I show you a picture right here, and I say to you, what is this? Well, if you say to me it's artifact, I'm going to say, yeah, but what kind? So what kind of artifact is this?
Wandering
baseline.
And if I needed to troubleshoot that, because again, how can I troubleshoot if I don't know what it is? So I can tell you it's wandering baseline. How am I going to troubleshoot that? I need to know what causes it. So what causes this?
Breathing.
Breathing can cause it. Electrode problems can cause it. Sweat, moisture, skin. Think about its movement of the electrodes. It's wandering around. It can't figure out what to do because it's not secure. You know, somebody who wanders around aimlessly really isn't like a secure in what they're doing. They're not just going for it. Like, you ever seen somebody walk like through the mall and they're just not really sure what they're doing. They're kind of all over the place, but somebody who's definitely getting to that, Black Friday sale is gone. They're straight, they're going. Like, they're not wandering anywhere. So you have to think, what's causing this? Like, it's not secure. The electrode is not secure. It's moving around. So that when you see that and you want to know what kind it is, then you would just, how about this one? Is this giving you
electrical?
Right. So yes, it's dark, it's thick. It's like so many electrical things going through at once. It's just ridiculously jammed up. But you can see the heartbeat, right? You can see that contraction is taking place, right? How do we know this? Here, here, here. That's what we're fixing to learn in the next chapter. But you see, if this was pretty and straight and clean, you would have your heartbeats, right? You would see it. But can you determine what kind of rhythm that is? No. You can tell. You can almost tell that they have a rate. Like, you can tell that's a pretty consistent, distance. So the rate is pretty good. But again, you couldn't say you could technically give that to somebody and read it. You cannot tell what that is. But you can tell it's electrical just by the fact that it's just so thick and dark. Why is it thick? There's so much activity going through there. How about this one?
Somatic.
Nope. Remember, somatic is kind of
broken
pattern, right? Does this have a pattern? Well, it kind of does here and it kind of does here, but here it's broken. It may even be gapped, but it's not consistent. So what do we think about that? Like, what do we do, right? What do we need to do with that? We need to check the wires, because if it's a broken recording, that means that it's not being transmitted to be able to be recorded, right? So then you think, oh, it's got to be the wires. So let's go back. He didn't hit up somatic yet. I mean, tremors yet. Where'd they go? Let's see. Maybe we didn't get down that far. What? Okay. Did I miss it? Like,
should have been the first one.
Was it the first one? Yeah, here it is. There. So we know that's artifact. Now, this is flipped, which again, it's just the lead placement, the directional placement, and we still know that that's a heartbeat. Now, when we start learning about atrial fib, you go look at that and say, oh, that's atrial fib. No, it's not. How can I tell? Y'all will remember that I said this later on when we learn about atrial fib, because this is too consistent. These heartbeats here, like they're too consistent. With atrial fib, these will be closer together, farther apart. Like this, it looks good, but it's not a consistent beat. So I know that this is artifact. because this is crap in here. And how do I know that? Well, look how consistent the tremor is. So the person's tremor is happening. Like, it's not broken. It's not thick. This is the person shaking. You can almost see the person shaking or the tremor happening, shivering. And again, we talked about all the things you could do for that. What can we do for somatic tremor?
Put their
Give them a
hands on the butt.
blanket.
Right? You can give them a blanket because maybe they're cold. Put their hands.
Have them lay on their hands.
Yep.
Turn up the room temperature.
Put their palms up underneath their back or their buttocks to like kind of hold them still. You just make them more comfortable. Maybe they're just anxious. Like that's. But again, if you look at these, you can tell what they are. Just think about what, that's junked up. This guy's all over the place. And if you know how to identify him and you know what causes
Okay, so how do you know? I mean, I understand you can see the electrical interference, but like, what do you do about it?
ask somebody to turn off their cell phones. Maybe everybody in the family's there on their tablets or their phones or
Okay.
that sort of thing. And you're not going to. Telemetry has come a long way, so you probably won't see this as much. But again, electrical interference, it can happen because you're trying to pick up the electrical activity of the heart. But everybody in the room, if the patient's got their cell phone right next to you, everybody's they're holding their cell phone with their hand while you're doing the EKG, and everybody else is on their computers. Sometimes it just picks it up. Maybe their heart's kind of weak. And so when you put those electrodes on to get a reading of their electrical activity, it's literally getting a reading of everybody's electrical activity in the room. So you just tell everybody to get out, take their phones out. That's all that's all you can do is try to fix that electrical problem. And again, if you can't get it to resolve, you refer to the manual, you get help, Best thing to do is refer to the manual. Anybody got questions about artifact?
Mm-mm.
And we talked about lead placement. So if you have a question on the test that asks you to draw out the lead placement, you would have no problem. Hopefully we can eventually get to the lab and do them. Scar tissue, how about babies? Everybody go with the babies.
Mm-hmm.
And what's different? Now, is B1 and B2 flagged on this baby?
They're going to be the same.
Yes. What if the baby has dextrocardia?
Opposite.
Right. You're going to flip them. What if I need to put these? Oh, here's a good question. If I need a posterior EKG on this baby, what am I doing? What am I going to do with them?
Put 4, 5, and 6 on their back.
On which side?
Right.
Exactly. Does everybody understand that one?
Mm-hmm.
It's going to be the same. That's a regular one. But if I'm doing it on the baby, I need to do it on the other side. Or a person that has dextrocardia. And this is what it look like. So if you need to do a posterior EKG and you pull this out of your machine, this is what you really want to, you want to document this, that it was posterior. You don't necessarily have to do this, but it would be a good thing to do it so that you're making sure they understand that this is a posterior EKG. Everybody got that part? You will see that again. Everybody knows these, the semi-Fowlers, what to do with the pregnant lady, that.
Mm-hmm.
Okay. Troubleshooting, always check your battery power supply, your paper supply. If it were me, as soon as I got there for my shift, I would do that. When you guys go to clinicals, that's the first thing you're going to do. Like, somebody's going to be with you, but of course they want to see that like what you're doing. And it's right off the bat. Like, I need to make sure I don't get into this patient's room and realize, oh my God, the battery's dead and they're too far away from a plug, or that it doesn't have paper, that I have expired electrodes. Like, that kind of thing. So you want to always make sure your machine and your equipment, whether it's mobile or it's not, is all like good to go before you even go in the patient's room. And before you go in the patient's room, what else do you have to have, Brianna?
The doctor's orders.
Go.
Wait, did you say no?
Yeah, I said no. Yes, that's right.
Oh, sorry. I was like, you said no. I was confused.
No, that was perfect.
My computer died earlier when you were talking to me. I was like hoping you like didn't think I just like got mad and clicked out.
Oh no, not at all. Oh God, if y'all get mad about that kind of stuff, then y'all are in the wrong profession. Because somebody will yell at you one of these days, and y'all will just have to just be like, oh, whatever. Chapter review, we went over all of that. Like, I think y'all are good with 7. So I'm gonna upload a test on 7 that will be for your grade, and it will be due before Tuesday at 6. But then you will also need to read chapter 8, and I don't know. You don't necessarily have to do the review questions before class on Tuesday, but they will be due by Thursday, and then we will continue on with 8. But we may have a quiz on 8 on Thursday because we're not doing the other, and 8 is very, very important. So everybody good with that? On 7, everybody's good? Everybody's gonna make 100 on the test and like rocket out their grade?
Mm-hmm.
Yeah.
Okay, that's good, because like I'm not giving y'all a pass on anything on 7. We've been over it, over and over it. Because really it's not a lot to 7. If you know your artifact and you know like your placement and your like those kind of things, that you won't have a problem at all. So let me see here. Share screen. Let's see. Everybody good? Anybody need a break? Anybody need anything? Let's see. I'm so used to saying that, like you actually couldn't just get up and go do something. I know, right? Okay, so can everybody see my screen about 8?
Mm-hmm.
Okay. So everybody, you need to read 8. Like, if I were you, I would go ahead and take my test on 7 after I reviewed it. I'll try to have it. What's today? Thursday. I'll try to have it on by Saturday morning. Yeah, that shouldn't be a problem. And then I would go ahead, if it were me, I would review 7 and then take it so you can read chapter 8 and like take notes while you read, look at the PowerPoints. I'll send this to you. I can send you the review questions, but if you don't turn them until Thursday, it's fine. So here we go.
Yeah, I would prefer that you already send them to me though.
Yes, I can have it done. Yeah.
As a go along, that's fine. I mean, I have them. I can send them out. I mean, that's no problem. Because when you go through 8, it's good to, take notes as you go, as you read, or go through the PowerPoints or whatever. And I'll try to send all the information I have on 8. I have a bunch of handouts because I remember this chapter we got a lot of handouts on this one. So I'll try to send them all out. So this is all a review at the beginning because we talked about this so much, but if you don't understand this concept, we cannot move forward with 8. So we all need to make sure we know the difference between the mechanical and electrical activity of the heart. What is the mechanical part of the heart? The what? When the electrical activity of the heart, what is mechanical? What's happening mechanically?
Pumping.
It's making the heart beat.
Right. Okay. Right?
Contraction and relaxation.
That's right. Contraction, relaxation. The actual physical part of the heartbeat. The heartbeat is mechanical. It's contracting and relaxing all the time. So it's the mechanics of it. It's it's working. That muscle, that thick muscle in the middle, that is contracting. That's the mechanical action of the heart. That is not electrical. Right? Has everybody got that? Mechanical and electrical, 2 different things going on. So vital to the mechanical, what do you have to have? Everybody see this? These 4 things?
Mm-hmm.
These are the components. If I ask you, what are the components of what do you have to have for your mechanical function of your heart to work correctly? So you have to have muscle, right? What else mechanically is happening? So try to envision the heart. It's when I say mechanical, that's the part that's physically moving, right? So what do you have to have? Those valves, right? What
Blood
else?
supply.
Right? And the blood vessels.
Vessels.
Right, because if your vessels are not functioning correctly, can the rest of it happen? No. So those 4 things have to be present and functioning for you to have normal electrical activity of the heart. So if I did an EKG on someone, I'm looking at their electrical activity, right? But it's
Right.
showing me mechanically what's happening. So if they had a heart valve problem or a heart muscle problem, if they had a heart attack and part of that muscle didn't beat right, it's not going to show up right electrically, right? Because there's a problem with it. So when we do that EKG, everything we've talked about till now, the leads, the electricity that goes through them, that's picking up that heartbeat and everything that's happening, because it all is sending out electrical signals. But it mechanically, this is what you need and what has to happen. So we all just need to make sure that you will see this again. So the difference between mechanical and electrical, and it says it right here, but the mechanical function relies on the electrical, right? Can you have mechanical without electrical? No. So in electrical activity, what's happening is cells are doing what? The cells are generating this electrical activity. Remember, potassium, sodium, all these chemicals going in and out that cause this electricity. If that's not working correctly, is the mechanical function going to happen?
No.
So we need that specialized tissue that creates electrical impulses that spread throughout the heart. They trigger the mechanical contractions of the heart. So again, like if you think about the electrical, like the lightning bolt hitting your house, it starts here at the top and it has to go down to a ground and it follows a pattern. And if you think about that, that's all electrical. But what's happening to your house? When your house gets struck by lightning, it literally, I mean, think about it, it contracts, like it moves. There's like a big, like earthquake. So this, in order for the mechanics of your heart to work, it has to have that electrical impulse. So it's just, they kind of work hand in hand. Cardiac output, I know we briefly talked about this before. So in the simplest terms, when you think about cardiac output, even if you didn't know what it meant, you would know, oh, it's the heart's output. Output is what? What does the heart put out?
Electrical pulse.
No? Mm-mm. What is the heart putting out of its left ventricle and aorta? Blood, right?
Blood.
Right. So cardiac output refers to the amount of blood that the heart pumps out each minute. So if I say to you, like, your cardiac output is bad, like, what does that essentially mean? Are you putting out enough blood to keep your body perfused and oxygenated? No. So cardiac output, it really is measured like minute, like how much blood is pumped with each heartbeat, or each, like, or what they call stroke volume, same thing, multiplied by the number of heartbeats per minute. Again, well, you have to know this, like, no. Basically, cardiac output, and if you just think about it, it's the amount of blood being pumped out with each heartbeat. So if my left ventricle is enlarged and it's not like pumping correctly, am I putting out enough blood to make it, like, make my feet perfused? No. So my cardiac output would be low. It's also called stroke volume. If you see stroke volume, volume is what? An amount. So it's stroke, don't think stroke is like CVA. Stroke is in like heartbeat. Every time, like, that heart strokes. I don't like that stroke volume word, but just think about cardiac output and what it means. If it's low, your health is going to suffer. Do you think ever you're going to see like the doctor say, oh, this patient has high cardiac output? No. Is that relevant, or is that going to cause? No, you're not. Your body's not going to, your heart's not going to pump out more blood than it needs. Like when it becomes a problem is when your cardiac output is low. And if that's too low, and sometimes they call it ejection fraction. So like if your heart, if it's too low, that's when a person might get a pacemaker because it's not beating correctly to get that blood out. So just remember that low output can be caused by electrical problems and mechanical problems. Does everybody get that part?
Mm-hmm.
Any questions about any of that? Your mechanical heart, electrical heart, they work together. Difference between the mechanical and electrical, they have to be met in order for blood to pump through the body. So if you don't have an electrical or a mechanical activity going on, are you getting blood pumped through your body? No.
No.
So the electrical system of the heart has to be working properly. The mechanical components, which are what? What are the mechanical components? It says right here, muscles.
Muscle and valves.
Those are your mechanical components. Those are the two things that move, right? If you just think about it in like those type of terms, it's your electrical and your mechanical. It's like the computer system in your car and the actual like pistons firing in the engine, mechanical and electrical. So those two things have to happen and for enough blood to pump through an intact vascular system, right? So because if it wasn't intact, if your leg was cut off, then would you be getting enough blood around your body? No, because it would be getting out. But would that be a mechanical or electrical problem? No. So does that make sense? That concept makes sense to everyone?
Mm-hmm.
Or does everybody just get lost on that one?
You lost me on that one.
Okay. What part lost you? Oops.
You said something about the leg.
So you clearly got lost on that one. Okay. What are the two things your heart has to have in order for it to get blood to circulate in your body? What kind of systems in place? What kind of activity? It's got to have electrical and mechanical. Right. So those are the two things that have to be working in order for blood to get circulated through your body. Right? Mm-hmm. So if your electrical impulses in the heart are working fine and your mechanical impulses of your heart are working fine, are you getting blood around to your body sufficiently to oxygenate?
Yes.
Mm-hmm.
Yes. If I get into a car accident and I have my foot amputated and I'm at the scene and I'm bleeding out, is my heart mechanical function still working properly?
No.
Yes, it is. Why is it not?
Yeah, because it's still trying to have homeostasis.
Did I have something happen to my heart?
No.
Nope.
Did I have something happen to my foot?
Yes.
So did the mechanical part of my heart get messed up?
No.
No. Did the electrical part of my heart get messed up?
No.
But do I have enough blood volume then to sustain life to the rest of my parts of my body?
Maybe.
No. Because if I'm bleeding out, is the blood being pumped to my body?
No.
No.
Right. So you're not getting enough blood volume to be pumped through your body. That's why it says enough blood to pump through an intact vascular system. Always read their questions like on your test, on your certification test. Read it for what it actually is saying. Enough blood to pump through an intact vascular system. Intact means there's not a problem somewhere else. I could see where that might be a trick question. Not for me. Even though y'all think I like a trick question, I don't. But again, I could see that being, because if you didn't actually read that for what it was, you might think, oh yeah. So you could be not perfusing and it be a different problem. Or say you had an aortic aneurysm that ruptured. Is your heart still beating as hard as it was? Yeah, until it doesn't get enough blood flow, then you're screwed. But for a few seconds, a few minutes, your heart is fine. Mechanically and electrically, it's fine. So if you're having a problem and you're totally healthy, say you didn't get in a car accident and you're not perfusing, then that's a problem in your electrical or your mechanical part of your heart. Because that's what you guys are doing, reading EKGs, is you're reading this electrical activity that is giving you a picture of mechanically what is happening. So does that make sense? Yeah. Until everybody understands mechanical and electrical, we cannot move forward, because that is the key to all of the rest of the stuff we're going to look at. So can everybody like reiterate mechanical and electrical activity of the heart and what exactly is happening? Yes?
No.
No. Okay. Why? Tell me what's confusing you. Explain it back to me, what you think, like what you're seeing here. Like,
I mean, like, the mechanical part I understand because the valves and the muscles are moving. The electrical part, so everything else is electrical with the heart?
what else is there?
Or I don't know. We ain't made it that far yet, but
Yes,
I mean, I
you
know
do
it's a
know.
lot.
But you do know. See, you're defeating yourself. You do know. You just told me the muscles and the valves are the mechanical parts, right? They have to work. Well,
So the vessels is the electrical part?
that's part of your, like, that's where the vessels aren't in your heart, are they? They're only on the outside of your coronary arteries. Remember we talked about the electrical was what causes electrical activity? It's that chemical change in the cells, right?
Mm-hmm.
So so your heart beats. How do you think your heart beats? What causes it to beat? You think just we were all born and this like muscle, it's really because your heart's a muscle, right? It's a little intricate, but my calf is a muscle. Does my calf beat? No. Why not? Because the heart has specialized cells that literally have a chemical reaction in these cells that causes electrical activity. And what does electrical activity do? It causes the heart to beat. It causes the mechanical components to work. So without the electrical activity, your heart wouldn't pump. So you have to have that electrical activity. What you're monitoring as an EKG tech is what? Electrical activity. I mean, it's a crazy thing to think about. And it literally is, if you like sat around and thought about it forever, you would just be so like, I love thinking about it, like reading about it, because it's so crazy to think that we are made up of cells in our heart that cause electrical activity that keeps our heart beating. It's like it's plugged in. If you unplugged it, it would stop beating. So these electrical impulses are what starts your heartbeat right off the bat. And it follows a pattern. It follows a flow. It starts in your SA node, which is at the top of your right atrium. And it literally kind of I always say it looks kind of like a lightning bolt, like through your heart down to the bottom. And that's the electrical activity. So you have those two different things that have to happen in your heart for you to have good cardiac output, for you to perfuse, for you to not, and that's why we talk about all the disorders, because if you have congestive heart failure, what's happening? Mechanically, your heart is not beating right? It's not strong. It's not being able to pump that blood, so it's backing up, right? So mechanically, you have something wrong there.
Mm-hmm.
So mechanically, it's just like a muscle. It wears out. Like that's why people don't live to be 200, because their heart, it just wears out. Like you cannot wear your muscle out forever. And that's why people abuse their heart, drug abuse and, obesity, smoking, diabetes, all these things that put more stress on your heart that wears out the mechanics. But again, if your electrical activity is not working properly, or the heart is dying, it's losing blood flow, or it's just not working properly, if the electrical activity isn't making that heartbeat, then it can't work. Now, it will help itself. Like, there are different points in your heart that this electrical activity flows, and say the SA node doesn't work to initiate that heartbeat. There's another place down below that will pick up and take over for it. So it's a system of basically homeostasis, where if that doesn't work right, this will. The heart's going to try to maintain itself electrically and mechanically as long as it can. But eventually, it stops working. That's why on an EKG, if you have a flat line, what is that telling you? There's no electrical activity. It's not that the heart's not beating. There's no electrical activity. There's no beat. There's no chemical change happening. There's no contraction of the ventricle. There's nothing happening. That's why it's always funny to me on like a TV show when they have a person who's flatline and they want to shock them. That's so inaccurate. So the next time you watch a TV with your friends and they go to shock somebody that has a flat line, you could say, that is totally ridiculous, because when you are shocking someone, you're trying to trigger that electrical activity to get back in order. But if you're flatlined, is there any electrical activity there? No.
No.
So you're not picking anything up because there's nothing there. What do you have to do in that part? You do CPR. You try to mechanically get that heart to beat because there's nothing electrical happening. So
we would be wasting our time doing it with the shocker.
Oh, yeah, you would never do that. Because again, there's nothing there to shock. If a person's in VFib or VTAC and they have some kind of electrical activity going on, then yes, by God, shock them, because that's going to you're trying to like shock that rhythm back to normal, because it should intrinsically beat regularly. It should be normal. But if it's nothing electrical left, if that's flatline, it's just crazy. Every time I watch a show that like, oh my God, the person's flatline, like shock them. What are you shocking? Nothing. There's nothing there. There's no electrical activity. You have to get some going by doing CPR and try to mechanically get that heart to beat, to kind of maybe just spark that electrical to start kicking again. But yeah, that's where you would not shock the person. There's no electrical activity. So your electrical and your mechanical basically are two working things. They work differently. And do you know what the difference is?
Mm-hmm.
So electrical is that chemical reaction that's happening in the cells. Mechanical is the actual mechanics of the heart working, the valves closing, the ventricle contracting, it's all the mechanical things working. Anybody have questions about that? Everybody's being so quiet. Oops. Everybody has that down packed now?
Mm-hmm.
Everybody's being so quiet. Did I just lose y'all, or y'all got it and we are ready to roll?
We're here.
I understand it.
Okay.
Yeah.
And don't overthink it. You guys are my overthinkers. Like this is a group of overthinkers, and I wish we were in class, because you would see I could hopefully make it seem a little bit more simple. But don't overthink it. It's just what's happening. That's all you have to know. Those two things. I got it. That's what's happening. Don't make it too deep. Okay, so we have to know this. This is a memorization, but I think you want to define this to yourselves and know it, because this is going to, like I said, everything in this class builds on each other. So we know electrical and mechanical, but then these are the words we're going to use and the things you're going to continue to use for like ever. So cardiac conduction system, when I ask you that, just break down the term. It's a cardiac conduction system. So if you're conducting, right, automatically it's probably something to do electrical. So that cardiac conduction system is the path of electrical impulses that control the heart's pumping action. It's just like I was saying, like the lightning bolt. It's a conduction of that electricity that controls the heart's pump. So Everybody get that, what cardiac conduction system is? We've talked about a lot of systems. Don't get mixed up with cardiovascular system. That's your heart and its valves and the blood vessels all like sending blood around. But the cardiac conduction system, when you see conduction, you think electricity. Where's that? Where are you finding electricity in your body? In the heart, right? That's what we're talking about. So does everybody get what that is? The pathway of electrical impulses. Okay. Your intrinsic rate, when we say intrinsic rate, each part of that system in your heart has an intrinsic rate. What do we mean by intrinsic rate? It is exactly that. It is what the heart is supposed to beat at, the rate that it's supposed to beat at that point in the system. So if you think about your heart, and you think about, like, I would say the lightning bolt through the heart or the house, it starts up here at the right atrium, right? And it goes down, down, down to the left ventricle. But up top, the intrinsic rate is a lot different than it is down at the bottom. So the intrinsic rate, what is normal heart rate for an adult?
60 to 100.
Right. So if I have a pulse rate of 60 to 100 and I'm perfectly healthy, where does that rate start? What determines that? My SA node or my sinoatrial node. You see where that says atrial? So let that remind you that the sinoatrial node, that little node that's responsible for your heart rate, is sitting there in the top of the right atrium. The intrinsic rate for your heart, what it should be, the normal intrinsic rate is 60 to 100. That is a normal rate. But if your heart doesn't fire at that SA node, say the SA node got messed up, like it just burn out, your heart's just not going to stop. There's going to be another spot that's going to pick it up, right? Each one has an intrinsic rate. It's going to actually get slower. So intrinsic rate is the normal firing rate of your heart's electrical conduction system. The SA node or the sinoatrial node, it's part of that system. It's located in the right upper atrium, and it is also called the primary pacemaker of the heart. What is the intrinsic rate of the SA node?
60 to 100.
Right. So if my SA node is the primary pacemaker of the heart, the intrinsic rate is 60 to 100 because that's the normal heart rate. So if you are a normal human being with a normal heart and a normal heart rate, it's coming from the SA node and it's 60 to 100. So if I ask you, what's the intrinsic rate of the SA node? You will automatically 60 to 100. And when we get further along, I'm going to say, what's the intrinsic rate of, the, bundle of his or, your junk? You'll be able to tell me that. It gets slower. It's different. It is different because it's not normal anymore. So your SA node or your sinus node, think about sinus rhythm is normal. Sinus rhythm, it's 60 to 100. It's when everything is normal. Your pacemaker is what? The pacemaker of the heart is your SA node. When we talk about a pacemaker, you can have an implanted pacemaker, right? And what is that doing? It's regulating your heartbeat, right? So if a person's heart can't function or beat on its own or beat regularly, they put in a pacemaker because that's going to keep your heart rate regular. So when I say the SA node is the pacemaker of the heart, without reading this down here, you can think, well, the SA node must be what keeps my heart regular, because that's what a pacemaker does. So something that regulates the heart's contractions, the natural pacemaker are part of that conduction system that with the SA node acting as the primary pacemaker when the heart is functioning normally. So an artificial pacemaker, it would be your battery-powered device that creates that electrical impulse to stimulate the heart to beat. So you have that pacemaker is creating this electrical impulse that causes your heart to beat at 60 to 100. Or you have your natural, normal SA node that you're born with that is causing your rate to be 60 to 100, and it is its own pacemaker of the heart. So what about all of this does or does not make sense? We're talking about the electrical part of the heart now, the electrical conduction system of the heart. So if I asked y'all what the cardiac conduction system was, right off the bat, you could tell me it's what?
Pathway of electrical impulses.
Right. Karen, are you the only one with me now? Everybody else left?
Y'all here.
I'm just overwhelming y'all.
Here.
Is everybody else getting this? Like, this is like these things. What do or don't you understand about this?
I understand that it just all goes together. Pacemaker is made to make your heart stay in rhythm, and your SA node is your one that's built into your body already.
And where's it located?
The right atrium.
Atrium.
So if I ask you, where does your heart beat start in a normal heart? Where is it?
SA node.
And where's that?
In the right atrium.
Right. So let's go back. What is your intrinsic rate?
It's the normal.
But what is that?
60 to 100.
So what is the intrinsic rate of the SA node?
60 to 100.
Right. So if I say this person has an intrinsic rate of 80, where is their electrical impulses firing at? Where's that starting?
The SA node?
Exactly. Because is 80 normal?
No. Yeah.
Yeah. So it's 60 to 100. Now, further along, but just keeping in mind, if this person's heart rate is 40, do you think it's firing at the SA node?
No.
No. So somewhere else along that conduction system is firing that heart. And that's where you start to have your problems. It's like, wow, it's not. It's at 40, then I know there's something wrong with my electrical system. So we know that the SA node that sits at the top of the right atrium, it starts off that electrical impulse, and it is intrinsically 60 to 100. And in a normal person with a normal heart. Now, can I say, oh, well, my athlete is at 52. Is he still firing? Yes, because that is a whole different thing. But we're talking about a person with a heart problem that you can clearly see on your EKG, and it's 40, then you know that it is not firing correctly. So that SA node, you just have to, like, I have to envision it when I think about it or talk about the heart and the heartbeat and the electrical activity. And for me, you have to figure it out for you. I always refer back to my lightning bolt. Like, it starts at the top of that right atrium, it hits that SA node, and it travels a path down through the heart. Because ultimately, mechanically, the last thing you get in that contraction, relaxation, the depolarization is that left ventricle, right? Like contracting and pushing out all that blood. So basically, that heartbeat or that electrical impulse went from the top to the bottom, and it made everything kind of contract and relax when it should, and the blood went out to the body. What keeps that all in check is that intrinsic rate of the SA node. So that's why you will hear it's the primary pacemaker of the heart. And all you have to know about that is that it's responsible for regulating the heart's contraction. It's responsible for being part of the conduction system that starts the pacemaker, the heartbeat of your heart, that whole one cardiac cycle. Because one cardiac cycle is what? contraction, and relaxation. And how does that work? By electrical activity, your cardiac conduction system. Is that clear as mud, or do we like not explain it? Y'all, ask questions, because we, this is different than being in a class, but you just don't overthink it. So does all that make sense? Clear as mud?
Mhm.
Yes.
Okay. So so we're moving. So you think about, we're still talking about the what? The electrical conduction system. We're still talking about that, right? So it started where? At your primary pacemaker, which was where?
And the SA node,
And it was located where?
right atrium.
Okay. So our lightning bolt is starting at the top and it's traveling down our conduction system, because what happens, like with your heartbeat, the mechanical side of it, it's contracting and relaxing. So when it contracts, it's what? Sending the blood, the electricity is sending the blood through your right atrium to your down to your,
Right ventricle.
Right, but you're going through the atrium. The atrium is the top of the heart. That's starting your heart rate. So when it goes, the electrical activity, the conduction system travels down. And SA node, the next thing it goes to is what we call the AV node, the atrioventricular node. Now, if you didn't know anything else, what would that word tell you where that node was located?
Yeah, atrium.
Well, what else is in that word?
Bottom.
Ventricle.
It's both.
So it sits right there at the atrioventricular, where they meet. It's the node there that captures that electrical activity and sends it on down, right? Because the heartbeat has to continue. The conduction system has to continue. So it's located at the bottom of the right atrium, right behind that little valve, right? That's going to let the blood through. It has an intrinsic rate of 40 to 50. Remember I said, if I asked you if the person's heart rate was 40, was their SA node working properly? No, because what's the intrinsic rate of the AV node is what we call it, AV node. That little node, when you look at it in the pictures in the book or whatever, like it's the next thing on the conduction system. So your heart rate, your electrical activity starts at the SA node, and it goes to the AV node, the atrioventricular node. So it has an intrinsic rate of 40 to 50. Everybody understand that? Like, it's different. Each node or junction or part of that heart has a different intrinsic rate. Because what is happening? It's contracting. You got all this force. It's got to contract. It's got to send that electrical activity down. But as it goes down, the force is going down. Everything kind of slows down. Like, so if you see a natural progression of a heart that's like in heart failure, that's dying, you're going from your normal heart rate, your SA node is working. And if you ever notice, you see it widens out, it gets slower. I mean, you can kind of see it go down the heart and die. So the AV node is sitting right there at the bottom of the atrium, right behind like the valve. You know what its intrinsic rate is. So then the next thing on your pathway is your AV junction. So that's a junction. We already know what a junction is. They're coming together. So it's part of that electrical conduction system of the heart that's located between the AV node and the bundle of His. That's what they call the next junction, is bundle of His. And that is part of the conduction system that's located in the upper part of that interventricular septum. It's also the bundle of His can also be called AV bundle. And that's kind of where it comes together, like the atrium and ventricle come together right there as part of the septum. It again has a rate of 40 to 50. So these are all just pathways of your electrical conduction system. Do you have to memorize them? Well, yeah, but it's helpful to memorize them in a way that you understand that that's just the flow of this electrical activity. So your AV bundle is also called the bundle of His, which I don't know why it's crazy, but again, so if you think about it, where does your electrical conduction system start?
In the SA node,
Exactly. And what is the intrinsic rate?
60 to 100.
And it travels where? Down to the
AV.
It's
AV node.
the
AV.
The AV node, right.
I didn't know what to call it. I couldn't say that word.
Atrioventricular or AV. See where it says AV right here? Atrioventricular?
Yeah, okay, AV.
AV node. So it goes from the SA node down to the AV node, right? And what's the intrinsic rate of the AV node? 40 to 50.
40 to 50.
Right. Then it keeps traveling, right? And
It goes through the junction
junction, right? It's got to keep on rolling. It's like a train. It rolls through the junction.
to the AV bundle.
Well, no, bundle of His or the AV bundle, right? And what's its intrinsic rate?
40 to 50. It's
Right.
the same as the AV
Node. Yep.
node.
So you see how it's traveling down and your intrinsic rate is getting different, but these are all kind of the same because they're kind of right there together. Does that make sense? Everybody good with those? We're just following a pathway, that's all. So here we go. We're going to go down the conduction system, and after we pass the bundle of His, then we have bundle branches. That's part of the electrical conduction system that divides the bundle of His, and it carries the electrical impulses to the walls of the ventricles. So you can almost see it as like it comes from the top right, it goes down, it goes down. Then at the bottom, you have a split where it goes to the ventricles. So it goes, that bundle of His kind of divides, and the electrical impulses like keep going. So you see a lightning bolt, it starts, and you know how sometimes it'll just like scatter at the bottom? Like it starts off as one big electrical like lightning bolt, and then towards the bottom it scatters. And that's kind of, think about, that's what's happening. The electricity is spreading out. So it's really thick at the top and then spreads out. So then so after that, you go down your Purkinje fibers, which is what they're called. I think that's always strange, but that's part of that electrical conduction system that divides from the bundle branches, like to the bottom. They're like the last thing on this conduction system. So they kind of sit in like the bottom of the ventricles. And look at their intrinsic rate. It's 20 to 40. That's pretty slow.
What do you call them?
Purkinje fibers. And look at their intrinsic rate. So do you think if your heart is beating at 20 beats per minute, do you think you are having good cardiac output that your body's getting?
No.
No. So if you think about your system, if you say, oh my God, this person's heart rate is now 20, what part of that heart is actually beating? The Purkinje fibers, right? Because you can't have a 20 heart rate and your SA node's firing properly. Like if they have a steady heartbeat and it's 20, you know that the Purkinje fibers are the only thing firing, and literally you cannot sustain life like that. So
pretty much you're dying?
Pretty much.
Okay.
You can do CPR, you can do, defibrillation, heart transplant, a pacemaker. But again, if you did nothing, so say we're, in a world where we don't have all this capability, then you could look at that heart rate and it's perfectly like regular. And by regular, I mean it is like beating, it's regular. It's not all over the place, but it's only 20 beats per minute. So then you should automatically be able to say that pulse is being generated at the Purkinje fibers, which are in the bottom of the ventricles, and that's it. I mean, they're the toughest part. You think about the ventricle, it's tough, it's big, pumps blood, it's, And if your heart has pretty much just given out, like they're going to be the last thing that's still going to try to contract and give out blood. But just like that lightning bolt, by the time it gets down there, there's not a lot of electrical activity to maintain a rate. So that intrinsic rate is 20 to 40. When it says irritable in this system that we're talking about now, if you see the word irritable or it irritates this, what we're talking about is along that conduction system. It's if you irritate something, it will generate an electrical impulse, maybe at the wrong time or the wrong location. So again, when I have a messed up heart, if I'm in VTAC, my electrical conduction system is all over the place. They shock me trying to irritate one of those sites to get it to go back in a normal rhythm. So when we say irritable, we're just talking about those sites along the pathway that can initiate like an electrical impulse. A lot of time it's wrong place, wrong time. So just know that when we talk about that, that's what we're talking about. Let me see, here's a good, does everybody see this? The direction of electrical impulses in the heart?
Mm-hmm.
Okay, so we already talked about this. What do you think this green little node is here? What is this?
That's the SA node,
That's right, because where is it?
right atrium.
That's right. So it's working normally. And look at your electricity. This is what I'm talking about. Like I have to think of it like a lightning bolt. But you see how it's going, like this fires an electrical impulse. So the electricity is going, you see these green lines? That's where it's going. It's going here. It's going to cause the left atrium to work. But look what's happened. It travels down the pathway to the AV node.
Mm-hmm.
You see that node? That's going to pick up the electrical because you've got electricity has to be conducted. Like it has to flow or else it just gets cut off. So it has to flow. It's going here to cause all of your, contractions and the heart to beat, but it's got to be picked up somewhere. So it goes down here to the AV node. Then where do we say it goes? So look at what the AV node, does it go off in all directions? No. You see this, where the AV node goes to where?
It goes to the junction, to the bundle of his.
And that's right here. Yep. And then that's where you branch off to your right and your left bundle branches. You're going to hear somebody talk about having a bundle branch block. When you look at an EKG, you can clearly see that they have a bundle branch block, which means somewhere along this branch, there's like a block. It's blocking that signal, and you can pick that up on an EKG. So if you look at this flow of electricity, then you're going down here to your AV junction and the bundle of His, right? What's the intrinsic rate of the bundle of His?
80 to 40.
Nope. What is it? You said it right at the beginning.
40 to 80.
40 to 50.
40 to 50. Why did I say 80?
Because we talked about 80. If your heart rate was 80, would that be normal? Yes, it would come from the SA node. But the intrinsic rate here is 40 to 50. And you see where the electrical impulse is going? To the left and the right ventricles.
Mm-hmm.
So that's your pathway. And then down here, this is your Purkinje fiber. You see the last thing here on this system? That's the Purkinje fibers. So your electrical impulses, your cardiac conduction system starts here. SA node, AV junction, bundle of His, they're pretty much in the same spot. Right and left, right and left, bundle branches, Purkinje fibers. That's the flow of electricity. We talked about the blood flow, now we're talking about electrical flow. Because you have to have electrical conduction in order for mechanical to happen, right? So if the electrical conduction is not happening, then the heartbeat is not happening. You've got to generate an impulse. And it all starts right here. If it doesn't start right there, it will start somewhere else along this pathway. So does everybody understand this, what this is showing us?
Mm-hmm.
Yes.
So just remember this. This is a good little reminder. Each conductive area of the heart conducts impulses at a specific rate, the intrinsic rate, which ensures the blood moves through the heart as it should. So the blood moves. We know the flow of blood. We know that the electrical impulses have to happen in a flow to ensure that that happens. So it all kind of comes together. It all is working for the same common goal. It's just they work separately. And this is that same picture, but now you can see your SA node, your AV node, your bundle of His, and which your AV junction is up here. But just know it's like right here when you get to the bundle of His, and then your left bundle branches, and your you see the numbers here, because they're basically stimulating this heart muscle to beat. Like when you put the electrical little electrode on like the frog's leg in biology class, and even though the frog was dead, it jumped. Remember the leg moved because you were shocking that muscle with the little electrode. Did anybody have to do that?
Mm-mm.
Oh, well, when we dissected a frog in biology class, you could take the little electrode and you could put the little electrical like shock to the frog's leg on the muscle, and it would cause it to like literally like move. Why? Because electrical impulses were stimulating that muscle to move. And that's
Was that a heartbeat?
no, I'm just talking like if you did it on its leg.
Oh.
Right, because by then it didn't have any blood to actually generate, right? But if you put it's the same concept here, because this is it's a muscle, so it's got to be stimulated. So it's getting a little electro probe right here from the SA node by those chemical reactions happening in those cells that are generating electricity. So that's why you think, oh, well, if I gave somebody a potassium injection, 500 milligrams of potassium, that's it. I'm going to put them out for life. Why is that? Because you have now just screwed up the electrical activity in this person's heart. It will kill it because that electrical, like the chemical reactions can't happen, and it makes everything stop. It's crazy to think that all of these things have to happen correctly for you. So no wonder so many people have heart problems. Like, think about all the things that have to happen for everything to be correct.
It's a lot.
It is. So but for us, we just want to think mechanical and electrical. What is happening in each? And they have to work together. The electrical is what we're recording, right, on our EKGs. We're picking up that electrical activity from lead 1 to lead 2 to lead, we're doing all of that, right?
Right.
So what is it picking up? This. This is what we're picking. Yes, this is what.
I think it's crazy how like giving the potassium will like stop someone's heart.
I know. I was thinking that off in my head. I was like, ooh, they offer the potassium shots and there's vitamins and stuff like that.
Well, no, because you need that. You need your heart has to have enough potassium and calcium and magnesium. It has to have enough of that in the right amounts to beat properly. So I'm sorry?
I know, go ahead.
No, so if say a person with like congestive heart failure needed to be on Lasix, right? And they were just peeing all the time. Well, all of their minerals and their vitamins are going to be depleted because they're just going to the bathroom all the time, right? So a lot of the people that are on Lasix also have to take potassium, because in order for your heart to beat right, it has to have potassium. It has to have the right amount of potassium, because too much or too little can really cause a problem. because again, those chemical reactions in the cells have to take place in the exchange of, potassium and calcium, but in a way that generates electrical activity. So if you're depleted, then it can't function normally. So that's why, like, if you run, you sweat a lot, then your body cramps. Think about and then sometimes you get like, oh, my heart is like irregular. You're dehydrated. Your heart, you can feel like your heart's irregular. It's just not pumping right. Because it has to have enough of everything, but it's a fine balance. So it's weird to think like I have to have, too much potassium could kill someone, but not enough could kill someone too. You have to have the right amount. So that's what that SA note, everything is happening appropriately to cause that electrical conduction system to start. And once it starts, then it picks up along the way. That's why if a person is flatlining and you do CPR, what you're really trying to do is get that heart to pump. You are mechanically moving that heart, hoping to irritate one of those spots that will kick in and cause your heart to beat. I don't care where it is along that pathway as long as it starts. Because once we can get some type of electrical activity to start, then you can try to shock it back into normal rhythm. Does that make sense?
Mm-hmm.
Clear as mud. And I think it's nice. We'll stop here, but just go back over this stuff and look at it and try to just picture it and review it how it makes sense to you. And like, I'll send y'all everything that I have as far as like the handouts from 8. But just try to move your way through it to try to really get an understanding of what's happening here and the intrinsic rate and the pathway, because that's going to be really important. This is what you're doing. This is your job. You are recording this electrical activity, and you need to be able to tell if there's a problem, and you will be able to do that. So if you have questions, give me a call or like send me a text or email or whatever, and I will actually go in right now and try to send y'all the PowerPoints from 8, even though we're not done with them, and the handouts.
Awesome. Thank you.
Thank
You're
you.
welcome. Y'all have a good one.
You too.
You too.
Bye.
Night, everybody.
Bye-bye.
Bye.
Bye.